Alright, chat, we gotta lock in. Because if you want to mew like Isaac Newton and develop a similar jawline to him, you gotta understand how to solve these Atwood's machine problems. And you're gonna be like, variable, why is there a mass on the pulley?
What? What the fuck?
That's not sigma. Well, the old Atwood's machine that you learned about with just basic Newton's second law, it was too basic, too simplified. You didn't brain max enough. This is the next level. This will get you that infinite aura that you've always wanted. So let's tackle this problem together. And you're going to see that this problem really is light work. Alright, Sigmas. So we have a Pulley system, an Atwood's machine system, with masses M1 and M2, 70 kilograms and 27.3 kilograms each. And we have this pulley as mass. It is a solid disk, and that's going to be important because we're going to introduce translational and rotational motion to tackle this problem. So we can all mew and we can all goon.
That's what she said.
All right. So let's read the prompt. Calculate the acceleration of the following Atwood's machine system, then calculate the individual forces of tension. Assume no air resistance of frictionless system, and most importantly, G equals 9.81 meters per second squared. So we need to remember two very sigma formulas. Okay, the first one, and I'm going to do it in brown. The first one we need to remember is that sigma, yes, sigma, F equals ma. Let me do that A a little better. Now you're going to be like, what the sigma does this mean? Well, if you remember, sigma, and yes, by the way, you're gaining aura just by saying sigma, if you're repeating after me. This, all it means is net. What does net mean? The sum of everything. This is just a summation of all the forces. That's what the net force is, okay? So the net force is equal to an object's mass times its acceleration. But we also need another very sigma that I'm going to write down here too. It's going to be that sigma, yes, sigma again, tau is equal to I alpha. And no, we're not alphas yet. We have to become alphas. Right now, we're probably betas at most, because we barely know how to tackle this problem. But by the end, y'all are going to become alphas. Okay, you can be like, well, what's the similarity between these two equations? Well, this first equation is simply Newton's second law. Yes, Newton's second law in translational form. The second equation is Newton's second law in rotational form. That's the only difference.
Oh my God! Wow!
Torque, which is what tau is represented by, yes, a Greek letter, because all Greek letters are sigma. Tau means torque, and torque is the analog, the rotational analog of force. I, which stands for moment of inertia or rotational inertia, is the rotational analog of mass.
And do you know what else is massive?
And alpha, which is angular acceleration, is the rotational equivalent of linear acceleration. So now that we have that out of the way, we can actually start doing something. First thing we should do is draw our free body diagram.
What the hell? Oh my God, no way.
Now, on mass M1, we're obviously going to have a force of gravity down, M1G. If I could write my G correctly, there we go. And then we're going to have a force of tension, FT1, upwards. Okay. And now on mass M2, we're going to have its weight, M2G, downwards, and a corresponding FT2 upwards. Now you're going to be like, wait, FT1, FT2, shouldn't they be the same? Well, here's the thing, sigmas, they're not. And I'm going to write it right here so y'all remember. FT1 does not equal FT2. And you're going to be like, well, why, bro? Why can't I just say the two are the same? That'll make the calculations easier, and I can be more sigma that way. Well, here's the thing. Here's the thing, little Timmy. We have a pulley that has mass. Before, in previous Atwood machine systems, we've neglected the mass. This has mass, meaning the forces of tension on both sides of the pulley are actually different.
What the sigma? What the sigma?
Bro.
What the...
Because this thing is going to spin. This thing weighs. This thing has mass. And it needs something in order to spin. So the forces of tension are actually not equal. So you can't make that assumption this time. But here's the thing. We can do this. Notice how, well, just by the numbers, M1 is obviously going to pull M2 down. And just by the relative size, as best as I could draw. Now, M1 is going to pull down. There's actually just going to be a force of tension, still FT1 right here. And there is going to be an opposing FT2 right here. Now you're going to be like, well, why does sigma is this important? That looks like a Z, my bad. Why does sigma is this important? Well, let's see. This pulley has rotational inertia, which means it needs a torque in order to angularly accelerate. A lot of people assume, a lot of people make this very, very negative or a mistake. They say that gravity is the force that causes the torque on the pulley. No, my friends. That's not sigma. That's incorrect. It's actually the force. It's actually the force of tension, or in this case, the forces of tension that act along this pulley. So, let me draw a cool arrow. If we assume that counterclockwise is positive, this is just by convention. If we assume that counterclockwise is positive, then FT1 is going to exert a positive torque. FT2 is going to exert a negative torque since it's pulling the opposite direction. It's pulling clockwise, the negative direction. So now, sigmas, we can write our first actual equation. Let's go! And I'm going to use a text box for this because it's going to be quite a lot. Using this right here, we're going to write this equation. Using the rotational form of Newton's second law, we're going to write this. The net torque, which is, as we just saw, Ft1, but sigmas, wait, you forgot something. What the hell is torque? Torque, if you remember, is just RF sine theta. That's all torque is, RF sine theta. And you're being like, what the sigma does that mean? You're taking your force, multiplying by the radius, basically this distance, and then times the sine of the angle between the force and the, in this case, the radius kind of acts as a lever arm, right? The angle between the force and, I guess, the thing that's rotating, right? Well, if you notice, the forces of tension, since they kind of wrap around this pulley, they always make a 90-degree angle, or they're perpendicular to the radius. So thus, we don't actually need the sine theta. Since if y'all sigmas remember your basic trigonometry, sine of 90 degrees is just 1. Sine of pi over 2 is just 1. So we can actually just say that torque, in this case, is just R times F. We actually don't need this, since we're dealing with right angles. So, and actually, let me make this a bit bigger. Okay, so Ft1, and don't forget to multiply by the radius, and the radius we're going to use capital R, and you're going to be like, wait, why does sigma not be plugging in the radius of 2 meters? What I would recommend, and this is to everyone, don't plug in those variables immediately. Do not plug in those variables immediately, sigmas. You actually have to kind of, I would suggest doing it after you do everything, after you do all the algebra, after you fry your brain, after you math-max your brain. Ft1 times R minus Ft2 times R, right? Ft1, the radius, Ft2, radius, is equal to I. We're actually given an I. Since this pulley is a solid disk, its moment of inertia is 1/2 mr squared times, oh no, what about alpha? Oh, I can't do anything with just alpha, but we're going to need one more sigma equation. And that is that the linear acceleration is just the radius times the angular acceleration. In other words, A is equal to R alpha. Now, if we divide both sides by R, you can kind of see that A divided by R is alpha. We're going to actually sub that in. Like that. And you're going to be like, well, what did that do? Well, we can begin canceling stuff. Notice how this R is in the denominator, this is in the numerator. Get rid of this. This reduces by power, so now it becomes 1. Now, we're going to do one more thing. This expression right here can actually be factored by R. So I'm going to just do this and just write it out, this could be factored to R ft1 minus ft2, which means we can actually cancel this R. Oh, wrong tool. We can actually cancel this R and this R completely. Meaning you could just do this and it'll do the same thing. So just showing you why this works. Which means we're left with this special equation. And this is going to be a very important one. And I'm going to do it in this color. ft1 minus ft2 is equal to 1/2 capital M A. This is going to be a placeholder equation, or an equation that we're going to use later, because this is important, okay? We're going to use this equation, the sigma equation, later, because we can't do much with it right now. To get this equation to work how we want to, we have to look at these individual masses again. So we already drew the forces. We already drew our free body diagrams on M1 and M2. Now we can just sum the forces like normal. So M1G is going to be the greater mass. And by the way, we're considering this direction, this downward direction, as positive. Just to make everything clear, downward is positive. So from this sigma equation, let me draw that a little better. You're gonna get this. For the 2, you're gonna get M1G minus FT1 is equal to, we're just focusing on the block, M1A. There you go. And this is just the acceleration of the block, right? But you're also going to get another equation. And I'm going to write it up here. If we look at this now, M2, FT2 is, well, if you consider this, it's going to wrap around. So FT2 is actually positive. Let's see. Is it bold? Or I don't know. FT2 minus M2G is equal to M2A. There you go. FT2 minus M2G is equal to M2A. Now what can we do with this? We could solve for the force of tension. So if we just subtract M1G from both sides, we're actually going to get that negative FT1 is equal to M1 alpha minus M1G. Right? So if we just subtract M1G from both sides, you're going to get that M1 alpha is equal to M1G. Now, we could just divide everything by -1, basically swap the signs, and you get FT1 is equal to M1G, negative M1G becomes positive, and then M1A becomes negative. This is another sigma equation that we're going to use. I'm going to mark it because we're going to need it later. Ready? Okay. So FT1 is M1G minus M1A. Cool, right? Now, what about this one? Well, this one's pretty simple. Since FT2 is positive, we just add M2G to both sides. Oh, sorry, sigmas. And you're going to get that F, let me bold this, FT2 is equal to M2G plus M2A. And this is going to be our third equation that we're going to use. Now, guess what? Remember this equation that we have on the top? We can sub these values in for FT1 and FT2, and then we could solve for A. Whoa! Really? Yeah, I'm serious. Now we're gonna have this master equation. Okay, let's write this out. FT1, let's sub it in. M1G minus M1A minus FT2 M2G plus M2A. Don't forget the parentheses is important. Equals 1/2 MA. And there we go. This is where everything starts coming together. Oh, and by the way, if you didn't notice already, the radius actually does not matter. So if you decide to use a shrink ray on this pulley,
Ah! Ha! I've got it! I've got the moon! I've got the moon!
or let it goon for a bit and it becomes bigger.
What did he say?
Well, it's not going to change the way we solve for the acceleration of the system. It's going to be the same. The radius is independent. It doesn't matter. So now we just distribute the negative, right? And we can remove the parentheses. So M1G minus M1A minus M2G. And remember, a negative and a positive make negative, so it's minus M2A is equal to 1/2 MA. Now the goal with this is we gotta make all of these, I say, you don't have to follow me, but I say this is the best. We move all the terms that have the shared acceleration A to the right with this 1/2 MA. So let's do that. To do that, we have to add M1A, if I could write. We have to add M1A and add M2A. See? So that way we have the G's on one side and A's on the other side. That way, we're going to get this. M1G minus M2G equals 1/2 MA plus M1A plus M2A. And now the fun starts to begin. Now we can start factoring. So we can actually factor on both sides of the equation. Let's factor G from the left. And you get G won't be multiplied by the quantity M1 minus M2. And on the right, they all have A in common, so we can factor out the A. And you're going to get 1/2 M plus M1 plus M2. we're almost done, sigmas. Last thing we gotta do is just divide this entire thing by 1/2 m plus m1 plus m2. That's it. Make sure to do it to the other side. I cannot write an m for my life. Oh, that's a tiny plus. See? Kind of like that. And guess what? This term now is factored. Since it's factored, you can only do it as it's factored. If this is factored, gets out, leaving you with just a. And this, well, you can't do that. Okay. And this is going to leave you with the final acceleration of the system. Yay! A is equal to G times M1 minus M2, all divided by 1/2 M plus M1 plus M2. And sigmas, this is the acceleration of the entire system.
Woo! Yeah, baby! That's what I've been waiting for. That's what it's all about. Woo!
A is equal to the quantity G times M1 minus M2 divided by 1/2 M plus M1 plus M2. But wait, we're not done. This is actually not our answer. It's actually just to calculate the acceleration. Now all we have to do is just plug in a bunch of numbers. Okay, let's get started. Let's plug in the numbers. A is equal to, what's our G? It's asking for 9.81, so let's do that. 9.81 times M1, what is M1? 70 kilograms minus 27.3. And I would put this in brackets on a calculator. Separate these. It's important. Divided by 1/2 of, what's the mass of the pulley? 30 kilograms. Plus M1, we already have 70. Plus M2, which is 27.3. And I would actually do this. I would put these like that. Yes, like that. And you're going to get that A. Let me skip a line for this. A is equal to, let's pull up Desmo, shall we? Let's plug this in to our calculator. You could just use double parentheses in decimals. 9.81 times 70 minus 27.3 divided by 1/2 of 30, which is 15. You don't need to calculate that if you don't want to. Plus 70 plus 27.3. And we get an acceleration of, rounded to 3 significant figures. A is 3.73 meters per second squared. And this is 1 part. Oop, not a good circle. This is 1 part of the problem. And by the way, if you saying, wait, why does this number seem familiar? 3.73. Why does this number seem familiar? Well, that's because of it. That's because it is. That's because it is. It's actually, fun fact, this is actually the value of G on Mars?
I'm a Martian, not a great white shark. I'm a Martian. I play frisbee in the park.
This is actually the value of g on Mars. If you go to Mars and you measure the gravitational acceleration there, it's 3.73 meters per second squared. But it's very close to 3.73 meters per second squared. For 3 sig figs, this is as close as you could get. 3.73 meters per second squared. So this pulley accelerates at the rate of g on Mars. Isn't that pretty cool? How sigma. All right. Now, we've only done a half of the question sigmas. Now we need to do the other half of the question. And that's calculate the forces of tension. But that's pretty easy. Because we already have 2 equations. But we can actually simplify them a little further. This one. Notice how they both have m1. So you can actually factor the m1. And you get this. ft1 is equal to m1 multiplied by the quantity g minus a. And this one up here is ft2. Let me bold it. ft2 is equal to, they share m2. So m2 multiplied by the quantity g plus a. And these are the 2 equations we're going to use to find the forces of tension. Okay. So let's do this on the bottom. Let's actually copy these. So I don't lose track of them. Okay. ft1 is equal to m1. What is m1? m1, if you remember, is 70 kilograms times 9.81 minus 3.73, which we solved for. And if you do that, 70 times 9.81 minus 3.73, 70. And watch this.
It's 70 times 9.81 minus 3.73. FT1.
70 times 9.81 minus 3.73 is 425.6 newtons. And remember, the newton is just the unit of force. I think we kind of already went over this. It's just a kilogram meter per second squared. That's all a newton is. Kilogram meter per second squared. It's mass times acceleration, right? Okay. We have the first force of tension. We can box this in. Second one. Let's do that now. Let's actually move this a little more to the side. Okay. Ft2 is equal to m2, which is 27.3 times 9.81 plus 3.73. Ft2 is equal to 27.3 times 9.81 plus 3.73. And let me make sure this is picking up decimals. Oh, good, it is. So 27.3 times 9.81 plus 3.73 is, we're going to round it to 4 sig figs, 369.642,646 newtons. And if you want to do a sanity check, you can just verify. FT1, which is this, minus FT2 should equal, we could actually get rid of these, should equal 1/2 of the mass of the pulley times the acceleration. And And look at that. If we just say just 3.73, we get pretty darn close. Of course, we rounded some things, but we're pretty close. 55.96 is basically the same as 55.95. We did it correctly, Sigmas. So, to reiterate, the acceleration of the falling Atwood machine system is the value of g on Mars, 3.73 meters per second squared. The individual forces of tension, 425.6 newtons on force of tension 1, and 369.6 newtons on force of tension 2. And this just shows that when you have a pulley that has mass, the forces of tension, which I already said in the beginning, they're not equal. Numerically, you can see that they are not the same number. And yes, we assume no air resistance of friction of the system, and that G is 9.81 meters per second squared. So Sigmas, this is how you calculate or how to solve an Atwood machine system with a pulley as mass. Very important in Unit 6 of AP Physics 1, which deals with torque and rotational dynamics. Very important in that unit. So if you're taking AP Physics 1, this is a great resource. And guess what? You math maxed, you physics maxed, you're now gooning harder than Isaac Newton could ever do, even with an apple on his head.
You didn't have to cut me off. I could never know we were nothing. I don't even need your love, but you treat me like a stranger, and I feel so loved. No, you didn't have to stop so long. How did I got you? To change your number. I said I don't need that though. Now you're just somebody that I used to know. Now you're just somebody that I used to know. Now you're just somebody that I used to know.
Congratulations. You're the true physics Sigma now. And that leaves me to see you on the flip side. Peace out, Sigmas. Voiceover variable here, and if you didn't believe anything I said in this video, I mean, I got a 5 on AP Physics 1.